We're ready to talk about chapter 6, and 6.2 is the standard normal distribution. Now, in chapter 5, we talked about different types of probability distributions or the basics of a probability distribution. We said that it could be given to us as a table, and in the left hand column, we would have all possible outcomes of an event, and in the right hand column, we would have the probability associated with each outcome, and all those probabilities had to add up to 1. In chapter 6, we're going to talk about normal distributions and specifically the standard normal distribution. But let me just mention a couple other types of distributions to you first. We've already mentioned these other types in section 2.3. The first is a uniform distribution where different possible values occur with approximately the same frequency. And I gave you this graph of the frequency of the appearance of digits in the first 3 billion digits of pi. In the first 3 billion digits of pi, there are the same number of zeros as there are ones, as there are twos, all the way up to the ninth digit. So you could say that the digits of pi are uniformly distributed between 0 and 9. We've also talked about a normal distribution where frequencies increase to a maximum and then decrease at relatively the same rate at which they increased. The graph is symmetric with respect to the center of the graph. The left half of the graph is roughly a mirror image of the right half. And an example of some scores that are normally distributed are IQ scores. The average of IQ scores is 100. It's right there in the middle, and the IQ scores are distributed about the same below the mean as they are above the mean. A uniform distribution may be used to illustrate the relationship between probability and area. Now, you have a problem like this in the homework. You're calculating the probability for a uniform distribution. For a New York City weekday late afternoon subway travel from Times Square to the Met Station, you can take the number 7 train that leaves Times Square every 5 minutes. Once arriving at the Times Square station, your wait time for the number 7 train could be anything between 0 minutes and 5 minutes, and every possible wait time is equally likely. Is wait time a discrete or continuous random variable? Well, to answer that question, just remember discrete random variables represent values which result from counting, and continuous random variables result from values which are measured. Since time is a measurement, um, wait time is a continuous random variable. The probability that your wait time will be between 0 and 5 minutes inclusive is what? You arrive at the station, there's a train coming every 5 minutes, so you're guaranteed a wait time between 0 and 5 minutes. Either a train is ready for you as soon as you get there, or you may have to wait up to 5 minutes, but certainly your wait is sometime between 0 and 5 minutes inclusive. That means the probability is 1. The probability of any given wait time can be represented by this rectangle. Um, your possible wait times are anywhere between 0 and 1. That gives you the length of the rectangle. And you can think of the rectangle as consisting of 5 smaller rectangles if you break them down into 0 to 1 minutes, 1 to 2 minutes, 2 to 3 minutes, and so on. What would the height of each rectangle have to be in order for the total area of the rectangle to be 1? We said the probability of a wait time between 0 and 5 is 1. So what would this height have to be if this entire rectangle was to have an area of 1? In general, for any rectangle of length L and height h, if L times h is going to equal 1, if you solve that equation for H, then H is going to have to be 1 over L, or for this rectangle of length 5, for that entire rectangle to have an area of 1, then the height of that rectangle would have to be 1/5. 1/5 times 5 gives you 1. So we have a rectangle that is 5 units long and 1/5 of a unit tall, and the area of that rectangle is 1. To find the probability that your wait time will be greater than 2 minutes, that's the area I have shaded here, a wait time between 2 and 5 minutes. Well, the length of the shaded portion is the difference between 2 seconds and 5 seconds. So the length, or in this case, I'm calling it the width, is 3 seconds, and the height we've already established was 1/5. 1/5 times 3 is 3/5, or written as a decimal, that would be 0.6. That means the probability that your wait time is between 2 and 5 minutes inclusive is 0.6. Now think about that. The exact halfway point between 0 and 5 minutes would be 2.5 minutes. So there would be a 50% chance that you would wait less than 2.5 minutes and a 50% chance that you would wait more than 2.5 minutes. If we bump that back to 2 minutes, there's only a 40% chance that you'll wait less than 2 minutes and a 60% chance that you'll wait more than 2 minutes. But that shows you that the total area under the curve between 0 minutes and 5 minutes is 1. Those two probabilities add together to give you 1. Just as we have seen that the probability of a given outcome for a uniform distribution can be represented by the shaded area of a rectangle, the probability of a given outcome for any distribution can be represented by a shaded area under a curve, so long as the area under the curve is 1. The area of the rectangle was 1, the area under a normal distribution is 1. We can use this concept, for example, to find the probability that a randomly selected pregnancy lasts between 238 days and 298 days if we know that the lengths of pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. For every problem that we do in this chapter, we're going to draw a normal distribution. In this case, the mean, which is always in the middle of the normal distribution, is 268, and standard deviation is 15 days. We're going to talk about how to find the probability that a pregnancy lasts between 238 days and 298 days. So we'll be looking for the probability that a pregnancy is complete somewhere in this shaded area between 238 and 298. Now we're going to talk about how to find that on the calculator, but think about something that you already know. How many days is 238 from 268? Or how many days is 298 from 268? They're both 30 days from the mean. And how many standard deviations would that be? Well, if one standard deviation is 15 days, then two standard deviations is 30 days. In other words, the 238 is two standard deviations below the mean, and the 298 is two standard deviations above the mean. What percent of the population do we know lies within two standard deviations of the mean, either two standard deviations above or two standard deviations below? It's the empirical rule that has already answered that question for us. If we know that we're looking for the probability that in a normally distributed population, a value lies within 2 standard deviations of the mean, that probability is 95%, or expressed as a decimal, 0.95 by the empirical rule. What if we weren't talking about exactly 2 standard deviations, or the empirical rule would even give us the probability for 1 standard deviation or 3 standard deviations? But what if we wanted a probability of something being, let's say, 0.736 standard deviations from the mean? How would we find that? Well, that's the task of the day. In 6.2, we're specifically talking about a very specific type of normal distribution called the normal distribution. And the normal distribution has 3 properties. Number 1, it's bell-shaped. All normal distributions are bell-shaped, so that's not special. But its mean is equal to 0 and its standard deviation is equal to 1. Now, there wouldn't be very much raw data in the world that would be represented by a standard normal distribution. Think about it. If the mean is going to be 0, then there would need to be the same number of values below 0 as above 0. They would all have to average out to 0. There's not very many real life data sets that are going to have as their average of the values or the mean of the values 0. So there are limited applications of this, but it allows us to talk about normal distributions which are not standard in section 6.3. The 2 things we're going to do in chapter 6 are we're going to find areas or probabilities. Probabilities and areas are synonymous. Find areas or probabilities corresponding to various regions under the graph of the standard normal distribution. In other words, for all the word problems, we're going to draw a standard normal distribution just like the one that I just mentioned, and we're going to be given some left score and some right score, and we're looking for the area between those 2 values, or the probability that a value lies within that range. The second thing we're going to do, if I give you the area, then I can ask you to find a z-score. For example, I can give you that the area to the left of this score is maybe 0.4 and ask you to find what that score is. And those are the only 2 things we're doing in all of chapter 6. Again, the standard normal distribution is a normal probability distribution which has a mean of 0 and a standard deviation of 1. The total area under the curve is equal to 1 because all of the values are going to lie within some number of standard deviations from the mean. We could go all the way out to 10 standard deviations below the mean and 10 standard deviations above the mean, but the empirical rule tells us that 99.7% of all values lie within 3 standard deviations of the mean. That's almost the complete area of 1 lying just between z-scores -3 and +3. Now, you can use some normal distribution tables that are in the back of the book to find the probability that a value lies between certain boundaries that I'm going to give you, but we're not going to use those tables in the back of the book for anything. So if you're working on homework and you get to an example and you click view example, and that hint from MyLabs Plus tells you to look at a table in the back of the book, that's not how we're doing any of these problems. I'm going to show you how to find this area on the calculator. I'm going to give you a standard normal distribution. I'm going to tell you, because it is a standard normal distribution, the mean is 0 and the standard deviation is 1. And then I'm going to give you some lower boundary and upper boundary and ask you to find the probability or the area of any randomly selected value lying between that lower and upper value. On the calculator, That is under your VARES menu, right above the VARES button on your calculator. It says distribution, DISTR, and to access the function that we need, I'm going to press second and VARES. And then choose normal CDF number 2, and I'm going to give the calculator the left boundary and the right boundary that I was given. Now, the reason that I'm using normal CD or normal CDF instead of normal PDF is, remember, the C stands for cumulative. It's adding up all the probabilities between the left boundary and the right boundary that I'm given. So I'm going to use normal CDF, and then I'm going to type in the left score that I'm given and then the right score that I'm given. All right, an example of a standard normal distribution could be thermometers that are using the Celsius scale. 0 on the Celsius scale corresponds to the freezing point of water. So if we were manufacturing thermometers, we would want the mean reading of those thermometers when in an ice bath, we would want the mean reading of those thermometers to be 0. That's what they're supposed to read at the freezing point of water. So let's assume that we have a lot of thermometers manufactured by the Precision Scientific Instrument Company, and the mean reading of the thermometers is 0, and the standard deviation of the readings is 1. Also assume that the readings are normally distributed. If we randomly select a thermometer, we want the probability that it reads between -2 degrees and +1.5 degrees. Well, it's supposed to read 0 degrees, but anything man-made is going to be a little bit off, and so we want the probability that a randomly selected thermometer has a reading between -2 degrees and +1.5 degrees. We're looking for this area within the normal distribution. Since we're looking for an area, we're going to use the distribution button, which is right over our VARES button. And second, VARES, choose number 2, normal CDF, and then simply enter that left boundary and right boundary that I was given. I want the probability that the reading is between -2 and 1.5. My comma is right over the number 7. I need to use -2, comma 1.5, and then enter. The probability that an individual thermometer will have a reading between -2 and 1.5 is about 0.910. That means that if I pulled very many thermometers from the ice bath and recorded their readings, 91% of them, just the 0.910 changed to a percent, 91% of them would have readings between -2 and 1.5. What about finding the probability that an individual thermometer would have a reading less than 1.27? Well, again, the mean reading on all the thermometers at the freezing point of water is 0. I want the probability that a particular thermometer has a reading less than 1.27. To which side of 1.27 would the mean be? 1.27 is a little more than the mean, a little less than 1.5 standard deviations. a little more than just one standard deviation from the mean. And we want the probability that a thermometer has a reading that's less than that. Well, less than 1.27 is to the left of 1.27. So that's the direction I've shaded. The only thing is when I'm using normal CDF, I have to enter a left cutoff score and a right cutoff score. I don't have a left cutoff score here. I'm shading forever to the left. Less than 1.27 would be all the way out off the graph to negative infinity, and I can't use negative infinity as a cutoff score. When that happens, we're just going to use such a small z-score that there really isn't going to be any area to the left anyway. For that very small z-score, when we shade forever to the left, we're just going to use negative 9,999 as our left cutoff. If we were looking for the probability that a thermometer would have a reading more than 1.27, we would enter positive 0.9999 as our right cutoff. But here I want to enter normal CDF. I'm shading from negative 9,999 up to positive 1.27. So this is exactly what I'm entering on the calculator. Second, Bayes, number 2 for normal CDF, left score negative 9,999, comma, right score 1.27. That probability rounded to 3 decimal places is 0.898. That means that a probability of a randomly selected thermometer will have a reading less than 1.27. The probability is 0.898, or if I change that to a percentage, 89.8% of the thermometers will have a reading below 1.27. If the thermometers are supposed to read 0 degrees at the freezing point of water, then about 90% of them at least are going to read below 1.27 degrees. If one thermometer is randomly selected, find the probability that it reads above negative 1.23 degrees. Well, think about where that would be in relation to the mean. The mean is 0, and a reading of negative 1.23 would be somewhere below the mean. I want the probability that a thermometer reads above that, so I'm going to shade to the right of that. And when I enter this information in normal CDF, I always have to enter the left score and then the right score. It always has to be in that order. So on the previous example, my left score was negative 9999 and my right score was 1.27. The numbers have to be in that order. And on this example, my left score is the negative 1.23, and I'm shading forever to the right. When I'm shading forever to the right, I'm going to use positive 9,999 as that right cutoff. So I enter normal CDF, second, Bayes, number 2. I want the probability from negative 1.23, comma, to positive 9999. And I get that probability to be 0.891 when I round it to 3 decimal places. That means the probability of randomly selecting a thermometer with a reading above negative 1.23 is 0.891, or about 89.1% of thermometers will have a reading above negative 1.23. So in the previous 3 examples, I was either given a left and a right score or I was given a right score and shaded forever to the left, or I was given a left score and shaded forever to the right. But in all three cases, I was looking for a probability, or a probability is the same as the area under the curve from my left score to the right score. But what if instead of looking for the area, I was given the area? Or instead of looking for a probability, I'm given a probability and I want to find the z-score that has that area to its left. Then remember, normal CDF gives me a probability. That's not what I want here. I'm going to be given a probability. I'm looking for a z-score, and whenever that is the case, I go one down below normal CDF on the VAERS menu or the distribution menu and choose number 3, inverse norm. When I choose inverse norm, I always, always, always have to enter the probability to the left of the desired score. In other words, if I'm looking for this z-score and I tell you the probability to the left is 0.7, then 0.7 is what you'll enter inside that parentheses. But if instead of giving you the 0.7, I give you 0.3, the probability to the right, then you're going to have to find the probability to the left and enter the probability to the left on the calculator. You always enter the probability to the left of the z-score that you want. All right, example 6 is using the same thermometers with a mean reading of 0 and a standard deviation of 1. Find the temperature corresponding to the 95th percentile. We have to think about what 95th percentile means. We have the mean temperature reading is 0, and we're not looking for a probability here. It doesn't say find the probability or find the area. It says find a temperature. A temperature is a z-score. And we want to find the temperature that separates the bottom 95% from the top 5%. Where do I need to make a vertical line if I want 95% of the area to be below it? It's going to have to be over here somewhere. I'm looking for this temperature that has an area of 95% to the left, or a probability of 95% to the left. Since I'm given a probability and I'm looking for a z-score, that's when I use inverse norm. And I enter the 0.95 because it's the area to the left of this z-score I'm trying to find. So second distribution, we're looking for a z-score, so we're going to use number 3. And the area to the left of the score we're looking for is 0.95. The z-score we're looking for, if we round it to 2 decimal places, is 1.64. If we use 1.64 as our z-score, then 95% of the thermometers will have readings below that. And that's what 95th percentile means. Now, just for the heck of it, let's prove, or let's say, if we were just given this z-score and the question was, what is the probability that a thermometer would have a reading below 1.64? If we were looking for a probability, then we would use normal CDF and we would say, what is the probability that a thermometer would have a reading less than 1.64? That means a reading from negative 9,999 up to 1.64. It's about 95%. These two operations, inverse norm and normal CDF, they undo each other. If I give you a z-score and ask you for a probability, then I should be able to check that by giving you a probability and making sure that I get back the same z-score. You use inverse norm when you're looking for scores. You use normal CDF when you're looking for probabilities or areas. 95% of the thermometers will have a reading less than or equal to that temperature we found, 1.64. If 2.5% of the thermometers are rejected because they have readings that are too low, and another 2.5 are rejected because they have readings too high, find the readings that are the cutoff values separating the rejected thermometers from the others. The word that tells me to use inverse norm rather than normal CDF is this doesn't say find the probability or area, it says find the readings. That tells me to use inverse norm. And on every problem in Chapter 6, I'm going to draw my normal distribution so I can determine what numbers to enter after inverse norm. The mean reading for these thermometers is 0. I want the cutoff scores that separate the bottom 2.5% from the rest and the top 2.5% from the rest. Let's talk about this bottom 2.5% first. There is some z-score that only has 2.5% of the thermometers with readings below that z-score. That percent, that's giving me a probability or an area. When you see percent, I want you to think probability, area, percent, same thing. That 2.5% corresponds to an area right there of 0.025. I want the z-score that has 2.5% or 0.025 to the left of it. Since I'm given that probability to the left, 0.025 is what I enter on the calculator. Inverse norm, second distribution, number 3, inverse norm, 0.025 is approximately negative 1.96. So if I use negative 1.96 as the cutoff for the lower end of acceptable thermometers, then only 2.5% of thermometers will be rejected for having readings below that. Thermometers will be rejected if readings are less than negative 1.96. And I could do something similar to find the upper cutoff score that only has 2.5% above that. Now there's two ways to find this, and you just need to be careful. If you have 0.025 to the right of the z-score you're looking for, then you have to forget this line for a second and say how much of the area is to the left of the z-score that I'm looking for, because I always have to enter the area to the left. Well, if the area to the right is 0.025, then the area to the left of that is 1 minus 0.025, or 0.975. To get this z-score, I'd have to enter inverse norm 0.975, because that's the area to the left, and that's what I always have to enter with inverse norm. Inverse norm 0.975 is positive 1.96. But actually, I should not have had to use inverse norm again because I know this is a normal distribution. I know there should be the same area to the left of negative 1.96 as there is to the right of positive 1.96. So if I've already found this z-score that has an area of 0.025 to the left is negative 1.96, then when I'm looking for this z-score on the right, I should know that it's going to be just the opposite of this z-score because there's the same amount of area to the left and to the right. Thermometers will be rejected if their reading is less than negative 1.96 or greater than positive 1.96. There's only one other thing in this section, and it is also finding a z-score, but it's a very particular z-score called a critical value. Critical values are going to be important in Chapter 8. So let's talk about what a critical value is. A critical value is a z-score on the borderline separating z-scores that are likely to occur from those that are unlikely. Unlikely. Common critical values are negative 1.96 and positive 1.96, and they are obtained as shown in the previous example. We're going to use other z-scores, but negative 1.96 and positive 1.96 are going to turn out to be very common numbers that you'll see. In the previous example, the values below negative 1.96 are unlikely to happen. They only occur in 2.5% of the readings. Or X values above 1.96 are unlikely to happen. They only happen 2.5% of the time. The reference to critical values is not as important in this chapter as it will be in Chapter 8, but we're just learning the notation and how to find it. So this expression, Z sub alpha is a critical value. And specifically, Z sub alpha is the z-score that has an area of alpha to its right. That's very important. If I draw a normal distribution, and I ask you to find Z sub alpha, because I'm asking you to find a z-score, you're going to use inverse norm. But the definition of Z sub alpha is the z-score that has an area of alpha to its right. Well, we just talked about inverse norm. When I use inverse norm, I can't enter the area to the right. I have to enter the area to the left. Well, if this area is, let's say, 0.2, then how can I find the area to the left? It would be 1 minus 0.2. If this area is 0.2, then this area is 0.8. Or if this area is alpha, then this area is 1 minus alpha. And because I always have to enter the area to the left, when I have the instructions find this z-score, I have to enter inverse norm, not alpha, but 1 minus alpha. Be very careful on the calculator, since inverse norm alpha would give me the z-score that had alpha to its left, and that's not what I want. I want the z-score that has alpha to its right. So I have to find the area to the left before I use inverse norm. Let's do an example of that. The directions simply say find the critical value Z sub 0.02 for the thermometers previously described. Now, what does Z sub 0.02 mean? That means find the Z-score that only has an area of 0.02 to its right. If it only has an area of 0.02 to the right, it's going to be over here somewhere. But again, the definition of this notation, this z sub 0.02, is that 0.02 is the area to the right of the z-score that I'm looking for, and that's not what I can enter in the inverse norm. If you give me the area to the right, I'm going to have to subtract to get the area from on the left, and that's what I'll enter in inverse norm. Not inverse norm 0.02, but inverse norm 1 minus 0.02. To two decimal places, that's 2.05. Now, if I could go ahead and say a dollar minus 2 cents is 98 cents or 0.98, then I could just enter inverse norm 0.98 on the calculator. But if I had a number I couldn't subtract from 1 in my head, then I can still enter inverse norm 1 minus that number, and the calculator will do the subtraction before it applies the inverse norm. Z sub 0.02 equals 2.05 means that the probability of a thermometer reading more than 2.05 is only 0.02, or only 2% of the thermometers will have readings above 2.05. It wouldn't be a very accurate thermometer if it was more than 2 degrees off. It's supposed to read 0 at freezing point. If it's reading 2.05, it's more than 2 degrees off, and only 2% of the thermometers would have readings above that. All right, I'm going to just let you take a break, and we will come back in just a minute and talk about section 6.3. The next homework assignment has both section 6.2 and 6.3 on it, so make sure you watch the next part of the video before you attempt the homework.